In this video, I'm going to show the image of why we need a signal integrity SI analysis in a 3D system, especially in the chip and IC packaging level. As we discussed last time in the white noise video, the deterministic interference will be part of degradation sources in signal integrity to reduce the signal-to-noise ratio SNR. For example, the reflection event not only reduces the signal power, but also has the reflection interference to add the interference on top of your signal. On the other hand, the high-frequency electromagnetic crosstalk will be another major source of the interference due to the big capacitance between any two lines. Therefore, the crosstalk will occur at the far end crosstalk between adjacent TX lanes, or at the near end crosstalk between adjacent TX aggressor lane to the RX victim lane. If both far end and near end crosstalk occur at the same time, the interference would degrade the link budget seriously. If we are aware of the importance of signal integrity from those two simple interference images, you will start to ask what kind of the signal analysis we could perform. Think about the frequency domain images for 5 seconds. Correct. To analyze the signal integrity SI in the frequency domain, we must check the insertion loss first. In addition, the channel or median loss through the cable or backplane should be clear to you from our several equation videos. But we haven't emphasized that the insertion loss of the die package must be included in the link budget estimation as well. Therefore, the left-hand side insertion loss show you a simple loss from the die side to the PCB side. As long as the insertion loss was taken care of in your link budget analysis, we don't need it to be much smaller, even though the smaller the better. On the other hand, the return loss will be related to impedance mismatch or reflection. Therefore, we may want the return loss as high as possible. But before we specify how good the return loss should be, do you think if the return loss analysis of the package only is good enough? Think about the interface images for 5 seconds. Correct. That was not enough, since there's an interface between the die itself or chip and the die package. Therefore, we must put both die and its package together and analyze it. From this differential topology of the TX and RX, there's still one subtlety of the differential operation. Think about the signal-mode images of the circuit operations for 5 seconds. Bingo! In addition to differential mode operation, the circuit must have a common mode operation for the DC biasing. Therefore, in addition to the differential mode return loss, we must check the common mode return loss as well to avoid the common mode reflection. If we are looking at both the return loss result, you might notice that there are specifications in both return loss, which is true for most protocol standards. Also, the specification of the differential mode return loss is usually 8 dB up to the bit rate with slight tolerance, and the specification of the common mode return loss is usually 6 dB up to the bit rate. Is this enough? Of course not. You should have a better idea that we should check the interface between the die package and the channel as well. Alright, what's left? Right, we need to check the crosstalk in the frequency domain through looking at the isolation between the aggressor and victim, which is the TX and RX respectively in this example. But we must check the package only and include the die as well, especially there's any inherently high frequency electromagnetic coupling sources, either from inductive or capacitive mechanism on the die. If you check the result very carefully, you may notice something. If not, think about the image of the subtlety for 5 seconds. Bingo! There's no specification here. So, what can we do? Excellent. This is like our insertion loss I mentioned a few minutes ago. Ideally, we want the isolation as big as possible to improve the SNR and reduce the bit array. But it's not necessary as long as the insertion loss or crosstalk was part of a link budget. And pass, please advise that we have a few link budget analysis videos in the I width, I high, and even 2D I analysis. Feel free to check those videos as well and let me know if you have any questions, and I will reply it as soon as possible. Is all the SI analysis in the frequency domain good enough? If not, what should we do? Bingo! Time domain analysis is a must. Simply as we did the SI analysis on chip either from the TX or the RX, we must simulate the I diagram in the time domain for both. Again, then we must add the simulated I width and I high result into our link budget to see if we could pass the target bit array. Is time domain analysis good enough here? Yes or no? The simulated I at the TX or RX in the time domain respectively should be good enough for the sanity check of the insertion loss and return loss in the frequency domain, but not the isolation or crosstalk. So what else should we do? Correct. You can simply set up a time domain test bench with the crosstalk by turning on all the TX actively to observe the I width and I high in each lens. Output TXDI I equals 1, 2, 3, 4, for example. Again, the setup looks simple enough, but do you see any subtlety here? Excellent. If all lenses are sending the same PRBS7 in the exact data rate synchronously, you might not be able to observe the crosstalk since the data transition is exactly the same to block the possibility of the I degradation from the poor isolation between lenses. So think about the asynchronous images for 5 seconds. Right, to create the asynchronous data transmission between lenses, you could apply different data rate and data pattern to skew the transition over time. For example, we could make the PRBS 7, 9, 11, and 13 with 32.1, 32, 31.9, 31.8 for a normal operation at the 32 gigabit per second crosstalk evaluation. After this crosstalk eye opening is done, how do we benchmark the degradation? Great, it's quite straightforward to just compare the eye opening of a single lens transmission without other lens with the eye opening of the lens bar active with others. Therefore, you can see a simple eye opening degradation in terms of the eye width and eye height as shown in the table. Then you can put the worst case of those eye opening degradation into your link budget analysis to figure out if that's too much or not significant. So far, we show all the basic SI analysis, and all results look good. What happens if you do see a big impedance discontinuity between your die and package? Right, you will see a reflection and the output waveform will be distorted. Here shows a simple image of how the 1010 pattern output waveform should be. But almost a half UI of the output swing is almost half due to the reflection. If you don't do any SI analysis, even though the on-chip performance is good, the circuit will still fail due to the poor package or PCB design at the interface to cause discontinuity and reflection to reduce the signal-to-noise ratio and increase the bit array. Hopefully, these poor SI images can emphasize the importance of the whole circuit SI analysis. Here is the summarized image you may have for why we need to perform a signal integrity SI analysis in a circuit system. The goal is to simply to reduce the bit array by increasing the signal-to-noise ratio (SNR), or someone call the signal-to-interference plus noise ratio (SNIR), to emphasize the importance of the interference or SI. Therefore, we must do the SI analysis through both the frequency domain and time domain. In the frequency domain, the return loss is very critical, relating to the series reflection. Therefore, most protocols have the specification to write the ecosystem to follow the differential mode and common mode return loss well. But the insertion loss and isolation or crosstalk will depend on different system requirements to meet the corresponding link budget. In the time domain, the eye diagram of each active lane can capture the insertion loss or the reflection well, which not only can help the link budget analysis, but also a sanity check of the insertion loss and return loss in the frequency domain. Unfortunately, this individual active lane cannot capture the crosstalk well, but the eye opening could be a baseline for a crosstalk benchmarking. Therefore, an eye opening of all active lanes are needed under an asynchronous operation between lanes by sending different data patterns and slightly skewed data rate. Lastly, we also show you an impedance discontinuity in the package design to cause the distorted waveform, such that the swing is almost a half, and the SNR degrades almost 6 dB to emphasize how important of the whole circuit SI analysis instead of just performing the on-die SI analysis. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefit from it.